Hi everyone, welcome back. So in this video we are going to understand the topic of radiation pressure in details. But before moving into the radiation pressure, I need to recapitulate two very important things that I discussed in the previous videos in the details, since those are very fundamental in nature and we can't understand the radiation pressure without those two topics. But let me derive those two things very quickly. First one is energy, average energy density, or later on we'll move to the average energy density. And second thing, we'll know about the momentum density, then momentum density or average momentum density. Because without this topic these two topics and this topic, you won't be able to understand the radiation pressure formula, or simply you won't be able to understand this topic at all. Okay, so let me start with the energy density. If you have seen those two previous videos, then you don't need to do the derivation, but I'm doing it for the new ones. If they are watching this video for the very first time, then let's go with the energy density, and I'll make sure that I'll try to do it very fast, maybe in 2 minutes. This electromagnetic wave is traveling along the z-axis, so electric field would be given by E naught cos of kz minus omega t plus delta x cap, because wave is propagating along x-axis, along z-axis, so this phase part will give that z, and polarization is along the x-axis, that electric field is oscillating along the x-axis, so polarization, this tells the polarization. So magnetic field will be given by B naught cos of kz minus omega t plus delta and y cap. Okay, this is the magnetic field direction oscillation. Okay, now energy density tells us energy per unit volume of an electromagnetic wave. How much energy is present in the unit volume? If I take here the unit volume of an EM wave, it carries some energy. How much energy is that? That will be present in the electric field and the magnetic field. So it is given by 1 by 2 epsilon naught E square plus 1 by 2 mu 0 B square. Okay, let's put the values of epsilon E square. How much is the E square? This is E naught square cos square. Let me write this kz omega t plus delta as theta. Okay, let me write the theta, that part. Okay, that will ease our calculations. 1 by 2 mu 0 in place of the B square, we'll write B naught square cos square theta. Now you can see we have cos square here, so this cos square is actually a sinusoidal term, so we must take into consideration the average. Let's take the average of this is energy density. Now we'll calculate the average energy density. Let me write it as this: average energy density 1 by 2 epsilon naught E naught square. Average of cos square is 1 by 2 plus 1 by 2 mu 0 B naught square. Average of this thing is 1 by 2, so it will give us 1 by 4 epsilon naught E naught square plus 1 by 4 mu 0 B naught square. I hope you understand this. This is the average of energy density, but since we know C square is 1 by mu 0 epsilon 0, which implies 1 by mu 0 is epsilon 0 C square. We also know that B naught is E naught by C, which implies B naught square is E naught square by C square. So let me put all these things here. So average of energy density is 1 by 4 epsilon naught E naught square. I'm trying to write everything in E and epsilon 0. So 1 by 4 in place of 1 by mu 0. This is whole 1 by mu 0. Okay, let me write it as the epsilon naught C square. In place of B naught square, I write E naught square by c square. This will go with this thing, so it becomes 2 times, or that 2 will cancel this 2, this 4, so it becomes 1 by 2 epsilon naught E naught square. So this is the average of energy density. Okay, this is the average of the energy density that this electromagnetic wave carries in the unit volume. Okay, let's say this is a unit volume. So let's move to the momentum density. Second part is the momentum density. I'm very sorry I couldn't finish in the 2 minutes, but yeah, that's actually very important in itself, so let's give it a bit more time. Momentum density is denoted by G, or like PD. So it tells us how much momentum is present per unit volume. Momentum per unit volume of an EM wave. Basically, when the electromagnetic wave strikes any surface, if I put here some surface, so basically when it strikes the surface, that surface feels the force, and that force exists only there if there is a change in the momentum according to in the Newton. So basically, if there is the rate of change of momentum tells us the force, so this surface feels the force, and it also feels the pressure. We call that as the radiation pressure. That force, that is possible only if the electromagnetic wave transfers some momentum to the surface. Okay, so basically the electromagnetic wave only transfers momentum to the surface if it carries some momentum, per unit volume. We call that as the momentum density. We call that as the momentum density. Momentum density is simply momentum per unit volume of an electromagnetic wave. So basically its definition is, I'm using both the notations. Okay, its definition is Poynting vector by c square. This is the basic definition. And what is Poynting vector? This is Poynting vector. I hope you know the Poynting vector. If you don't know, if you do not know the Poynting vector, let me tell you what is a Poynting vector. Poynting vector is actually, it is the energy flow per unit area, per unit area, per unit time through a surface, through a surface. So basically, if we put some surface here, what is and take here the unit area, that is 1 centimeter square, and we watch it for the 1 second there, that is the unit time. How much energy does flow through that unit area in the unit time? That gives us the Poynting vector. And Poynting vector is given by actually 1 over mu 0 E cross of B. Okay, but since again this E and B contains cos, and if we do the cross product of these, let's do the cross product. So Poynting vector is given by 1 over mu 0. This will give us e naught cos of kz minus omega t plus delta x cap, cross product with the b naught cos of kz minus omega t plus delta, it's y cap. Okay, and it will come out this e naught and the b naught. So e naught b naught by mu 0, it will give us cos square kz minus omega t plus delta, and it will be along the z axis, and obviously because x cross y will give us z, and obviously that Poynting vector will be along the direction of the propagation. So that energy flow will be in the direction of the propagation, not in any other direction. So it gave us correctly the z cap. Okay, now since there is a cos square, this is oscillating term. If this is oscillating term, that means we must take average into consideration, because we have to check in a one complete cycle how much energy actually does transfer through the surface. So let's take the average of the Poynting vector. So that would give us e naught b naught 1 over mu 0, and this will be 1 by 2. There is no problem because average of the cos square is 1 by 2. But again, we'll use 1 by mu 0 as here epsilon naught c square. So it would be epsilon naught c square, e naught square is there, 1 by 2 is there, and in place of b naught we'll use e naught by c. C will go, so it will give us 1c comes outside, 1 by 2 epsilon naught e naught square. I believe there is only one e naught. Okay, E naught square. So C into, can you tell me what is this 1 by 2 epsilon naught E square? It is the average of energy density. So basically, average of Poynting vector is this thing. This is the average of the Poynting vector. So now if we calculate now, momentum density average, or like this is the momentum density average, that would be average of the Poynting vector by C square, the basic definition I'm using here, and average of the average of the Poynting vector, sorry, let's go with this PD. Okay, let me use only one now. So average of the momentum density equals average of the Poynting vector C times average of the energy density by C square. So it will give us average of the energy density by C. So average of the momentum density is actually average of the energy density by C. This is one of the most important formulas, okay, for this topic. This is actually the momentum density in terms of energy density. This is Poynting vector in terms of energy density, and this is energy density basic definition. So now let's move to our main topic. What is radiation pressure? Now, what is radiation pressure? So basically, when this electromagnetic when this electro sorry when this electromagnetic wave when this electromagnetic wave when this electromagnetic wave strikes the surface, okay, let me copy it there, let's put it here. Okay, now, sorry, what I did, paste. Okay, so this is the electromagnetic wave traveling. Now if we put some surface, so let's say this is the surface there, okay, this is the surface there, and now we have two cases. Why? Because this surface could be perfectly absorbing. It could be perfectly absorbing, or it could be perfectly reflecting. Now let's understand the radiation pressure in this case. So when the electromagnetic wave strikes this perfectly absorbing surface, because it carries now the momentum density with it, that momentum density actually strikes, so electromagnetic wave actually transfers the momentum to the surface, and because of that momentum transference, it feels force. This surface feels force. That force per unit area, that force per unit area gives the radiation pressure. This is the radiation pressure. P is radiation pressure. So basically, radiation pressure is the force per unit area held by any surface, any perfectly absorbing surface or the perfectly reflecting surface, when the electromagnetic wave that carries the momentum density in it transfers some momentum to the surface. Okay, because of the so there will be change in the momentum, and that change in the momentum will lead to the force, because rate of change of momentum will give force. So basically, we're interested in finding the change in the momentum. Then we will do divide by time, so that would give us the rate of change of momentum, that will give us the force. Then we will divide by the area, that will give us the radiation pressure. I hope you get the idea. Let's take here, let me take it here, some, this is some surface, this is some perfectly absorbing surface, and electromagnetic wave comes there and it strikes it. Basically, this electromagnetic wave carries in it momentum density. I told you the formula. What is the momentum density? This is the momentum density, average of the momentum density that it carries in it. Okay, so it 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 actually travels inside this surface. Let's assume that it travels for the time del t, okay, with the speed c del t, with the speed c. So this distance would be c del t. This distance is the C delta, and let's say this is the A area of this surface. Okay, so how much is the momentum, how much is the momentum that got transferred into the surface? That would be this, the total momentum transferred, total momentum, total momentum transferred. So that would be momentum density, how much is the momentum present in the unit volume into volume. Okay, or let's say average momentum present in the unit volume into the volume, and average momentum density we know into volume, how much is the volume? That would be A C delta, because A is the area of this thing and C delta is the distance it travels. Okay, before it gets perfectly absorbed in it, because this is the a perfectly absorbing surface. Okay, this is the perfectly absorbing material, perfectly absorbing material. So this much of momentum, this whole lot of momentum will be transferred to the surface. This is the momentum per unit volume, average momentum per unit volume present in the electromagnetic wave, and this is the total volume that momentum traveled. Okay, or the whole volume contains that much of momentum density, total momentum. Okay, because momentum density into the volume will give us the total momentum transferred. Okay, so this is the total momentum transferred, momentum density into the volume. Different books write in a very different way, but I have understood this way, that total momentum transferred would be the total momentum density, how much momentum is present in the unit volume into the volume. Okay, so basically this much is, we can call this as the transfer of momentum. This is transfer of momentum. So it will be uh, average of momentum density and A C del T. And if we want to calculate the force that it exerted on the surface, that would be transfer of momentum, change in the time, or change in the momentum due to change in the time. So it will be momentum density A C del T will go. Again, this is a force. If we want to calculate the pressure now, radiation pressure would be force divided by area. So it would be momentum density into C. A will go. So this is the formula of radiation pressure. This is the radiation pressure equals C into the average momentum density. And if we write the P radiation in a very different way, so C average of the momentum density we calculated as average of energy density. Okay, so average of energy density divided by C, average of energy density divided by C. So C will go, it will be average of energy density. So P radiation is equal to energy, average of the energy density. This is again very important formula. This formula is very important. This formula is very important in itself. Okay, there is another term I should right now tell you, which is called the intensity. Okay, intensity, intensity, I, which is basically C times the average energy density. Okay, if you don't know, I have given a one video on this intensity. Okay, so basically we can replace this U as I by C. So I by C. So basically P radiation, or the radiation pressure, equals I by C. This is again very important formula. So fundamentally what we have to remember is this one, I by C, and this thing, average of the energy density, or C times the average of the momentum density. So this is for the uh, perfectly absorbing surface. For the perfectly reflecting surface, now if this is a perfectly reflecting surface, electromagnetic wave comes and electromagnetic wave goes. So change in momentum, change in the momentum here, it will be 2 times this. It will be 2 times of this thing. So basically it will be 2 times. So 2 will be there always. So here it will be 2. So basically P radiation for second case is for perfectly perfectly reflecting surface. Reflecting surface. So basically two will be there. So radiation pressure equals 2c average of the momentum density. So P radiation equals so it will again give us 2 times average of the energy density. So again it will be here 2 times U, and it will be 2 I by C. So P radiation equals 2 times I by C. So sorry. So basically all these formulas are very important for any competitive exam. I hope you understand the topic. If you felt any difficulty in anywhere, you can write the comment, or you can go and have a look on the videos I posted previously on this topic, or on this chapter. I have done a detailed discussion on every single term: Poynting vector, energy density, average energy density, intensity. Every term has been discussed in the details. So basically that's all for the video. Thank you so much.